Hi, it's Terry Denery of the MathWorks. Anyways, we're going to continue our conversation about field-oriented control, but in this video, we're going to focus specifically on this feed-forward piece. And so, before we kind of jump into the whole electric motor thing, I thought it'd be good to kind of conceptually talk about feed-forward. So, feed-forward is about kind of having really, really good a priori knowledge. You might call it kind of the perfect, knowledge or information of kind of the system that you're going to control, and very, very good information, let's say, of the environment in which it's going to operate. And then finally, let's see, very, very good information what this system is going to do. Okay. And I think we see examples in nature and just in the world in general of really, really good feed forward systems. And so for whatever reasons, I've been kind of thinking about sports and I've been thinking about golf and baseball. And what I think is really interesting is that, obviously, professional baseball players are good athletes, but you would tend to think that the really good golfers among the professional baseball players would be the guys that are really good hitters. Well, it turns out that I think more often than not, it's the guys that are really good pitchers, right? And I realize that this is kind of a feed forward thing, right? And that, just to be kind of, you know, probably oversimplifying it, but, if you're a pitcher, you know where the strike zone is, and it's not changing. It's the same this year as next year, and so forth and so forth. Okay, so you have very, very good information essentially of where you want the ball to go, right? Well, golf's sort of like that too, and opposed to kind of like throwing a ball, what you're doing is you're swinging a club. You're swinging a club such that that club face really hits that ball perfectly, all right? And so in the case of golf, it's really about you put a ball on a pin, it kind of stays there, and you have extreme confidence, right? That it's not going to move as you go through the motions of your swing. So anyways, the idea of I'll call it the strike zone, as well as kind of the location of the ball, that you have a good understanding of where it is, and therefore you're not reacting to it, and therefore you're really giving it very little thought, and you're not updating, I'll call your processor, your head with new information about what it's doing, right? And I'd say that the ramifications of that are all kinds of things that are kind of interesting. In general, it means that you can prepare very, very well for the mission at hand, with the feed forward system, as you can with regard to hitting a golf ball or throwing a pitch. And that you can train yourself to be very, very good at it too. So anyways, with those thoughts in mind, let's kind of move into the electric motor now. And I'd say the good news is that electric motors aren't anywhere near as complicated as swinging a golf club or throwing a pitch, right? But it does begin with good understanding of what it is, right? And so you'll see with our electric drive block, we tell it what it is, that this is kind of stuff you get straight out of motor catalogs, and so for a given voltage rating, there will be a stall torque, how much torque it exerts when the shaft is, not moving, and that's the max, right? What's the maximum speed it can reach? It's called the no load speed. And then turns out that this kind of implies things that allow you to calculate things like resistance in your circuit, and then there's this thing called the flex linkage, which is kind of a measure of how much torque the motor can generate, and then inductance, and then the number of pole pairs are additional parameters we put in here, all right? And so I guess all I want to really kind of say at this point is I think it's amazing that just a small set of information, this small set of content, if you know these parameters, you can describe pretty much every three-phase AC motor that's ever been created, right? So anyways, with this in mind, let's kind of jump into this, all right? And so of course, from that description we've provided, we're able to assign the motor, and we define its resistance, inductance. There's our flex linkage right there, and there's the number of pole pairs. And what may not be expected, we in the previous video, we talked about field-oriented control, and it was mostly about geometry and vectors and, projecting vectors onto like XY axes and ultimately coming up with really interesting transforms. Well, that information is being passed into this too. And we didn't see it in the previous video, but we're going to see it a lot as we get into the the feed forward piece of this controller. So last week was essentially going from, I call it this ABC, physical space orientation of our electric magnets that are in our stator, and essentially representing them with I call it a mathematical model that reflects the torques and magnetic fields that they can generate. But it's this idea of essentially observing and expressing, I'll call it your dynamic equations, and there is this vector nature to anything that drives a force or a torque, but viewing it from the perspective of the rotor of the electromagnet. It's through that we get this kind of D and Q orientation, right? And so that's quite a remarkable thing. It simplifies the math tremendously, and it puts us in kind of the natural space for developing the controls for an electric motor. Right, and then it really comes down to let's get the right direct current, let's get the right quadrature current, right? And these two things essentially will set the magnetic fields and therefore the torque that we're going to get out of the motor, right? Well, here's this piece called feed forward, right? And if you zoom in pretty closely down here, you'll see that our D voltage is really a summation of what we're getting from feedback from our PI controller, and that being added to the piece that we're getting out of our feed forward controller, right? So that's really interesting, and we're going to kind of examine that a little bit as we kind of move through this, right? But let's go ahead and jump in. I guess it's always interesting. Actually, let's look at the interfaces. It's always good to kind of look at interfaces. So feed forward essentially takes the ID current. Actually turns out we're taking ID current as well as the first derivative. We're going to talk a little bit about that too. The angular velocity and then the IQ current. So essentially this is defining, we've already told it what the motor is, but this is kind of telling, the controller this snapshot in time, what's really happening with the motor. And really that state is really kind of the electrical state is expressed extremely well and very efficiently by the currents, ID and IQ. And then mechanically, it's stated quite well by the shaft or the shaft angular velocity, right? So let's go into feed forward. We'll see that the upper block calculates V sub D and the lower block calculates V sub Q, right? And I think this is really interesting, and my point here is, we're not seeing any integrator blocks, we're not seeing any derivatives. All we're really seeing here is a simple algebraic calculation based on, again, the states of the system, which are going to be expressed by the currents and the angular velocity, right? And I want to give you a little bit of credibility, or give you a little bit of where this comes from. And where I've learned this is from the help on the permanent magnet synchronous machine block that comes with SimScape Electrical that we're using in this model, okay? But the electrical current dynamics is expressed by these two differential equations, right? So here's where I want to, really kind of hit this idea of feed forward, right? That if we really got the system operating the way we want, well, we know that we want to drive the direct current to zero, right? And hence we want its derivative to go to zero. And we know that we want the quadrature current to essentially reflect the torque that's going to make the system move the way we need it to move. And it turns out just knowing how we want it to move and knowing what it is and essentially what that mechanical load is, we understand a relationship between commanded motion and the quadrature current, right? And it really comes down to, if this is true, well, let me put it this way, all right, that if we know all this kind of stuff, and you look at these equations, the only thing we really don't know is what the direct voltage is and the direct voltage and the quadrature voltage. And so a simple kind of rearranging of these equations, we solve for those things. And essentially we no longer are solving a differential equation, but an algebraic equation where we know the derivatives because we have very good understanding of what the system is and what we want it to do. All right, and so again, I said we want ID to be 0, therefore its derivative will be 0. Simplifies this equation tremendously. All right, so turns out for our motion command that we know everything we need to know about IQ also. And so I'm going to do one more slide here, and I just want to kind of express this idea. Okay, so it's a little more complicated than this, but certainly it's this point that IQ will be proportional to the torque, and that for a constant inertia, it all comes down to how do we want it to move. All right, and so we're commanding a smooth transition on the angular velocity. Hence, we're going to know that that the acceleration will be finite because this could be this first derivative of the angular velocity. All right, now because we do have some DI/dt terms for quadrature, it turns out that it needs to be even a little bit more smoother than that, meaning that next derivative up, the one beyond acceleration, which happens to be called the jerk, okay, that needs to be finite as well, okay? And all I want to say with regard to this is, well, we know how to do that, okay? That we know how to do the math on this, and therefore, having an omega where these requirements are true is about making a very good choice on what you want the transition to look like on going from rest to whatever speed you're going to move it on. At least for the particular problem we're working right now, which is an electric motor that's driving a constant inertia shaft. All right. Okay, so let's get back to the model. And I guess I'll go right here. Now I'll go right here. Right. And let's hit space bar. Let's make it a little bit smaller. Let's push it out of the way so you can see both me and the model. All right. And anyways, we ran that model. Now I want to show you a couple of things I think are really kind of neat. All right. And so here is the scope. We got a similar scope on the quadrature voltage, but basically the feed forward is the first component going into the scope, and the feedback from the PI controller is the second one. That means the feed forward's yellow and the feedback is blue. All right. And isn't that remarkable? All right. It's like the feed forward is almost doing everything. All right. And it kind of reminds me of a really interesting visit to a customer who works for one of these big forklift companies. And he's been doing this for like 10 or 20 years, and he really knows a lot about forklifts, but he's a controls engineer. And so he showed me a plot that looks a lot like this for one of his controllers. And then he made this comment. He says, if I'm really doing my job well, my PIDs do nothing. And I thought, well, that's a very remarkable comment, right? But I think what it does really kind of tell that's very important is this idea of a priori knowledge of what the system is and what you're asking it to do, and essentially asking it to do something that's capable of doing. And if that's the case, you can often see something that looks like this, right? And so anyways, just to be really clear on this point, certainly continue to use PIDs. They're incredibly important, and they're incredibly important at what we're looking at right now. And I want to make that point right now. Right, so let's go here. And so I'm going to break up, what's being plotted here into two separate scopes, right? And so we already saw that, most of the calculation or the contribution to the direct voltage is being expressed right here, and that this is really a small fraction what we're seeing here with regard to the amplitude of oscillation. But what we're seeing is a couple of really important things, right? And I'd say it's this kind of back and forth that kind of looks like noise stuff that's going on before you get to this bigger activity of the PID controller, right? And so the other thing really is that bigger activity of the PID controller. And I'll first bring your attention to it synchronized perfectly with this point, right? And what we see here is that this is a real, I'd say, singular inflection point on the direct voltage. And haven't exactly dived in, truly figured out, what that represents, beyond the fact that I know it's also synchronized with our motion command, where we essentially bring the shaft up to 10 rotations per second. And it's at this point that we tell it stop accelerating. Okay. So I think if we looked at it, we'd probably see something that's associated with inductance or whatever, anyways, my main point on this is that whenever you get something that's kind of like a kink in your curve, PID controllers are really helpful for you in dealing with that, right? So that's one reason the PID controller is important. Okay, the other one though, and this is more, well, I think I'll say it this way, all right? And I wish I had a better version. Well, I'll use a blue pen. Maybe it'll show up a little bit better. But a better version of the inverted pendulum idea. Okay. But the basic idea, and I think that it is a classic problem for lots of reasons. One of them is that it's very interesting. And it's kind of obvious to anybody who watches an inverted pendulum, remain vertical. We know that something kind of magic's happening. All right. And we know that because we kind of know that naturally it's unstable. That as soon as it starts to tilt, and if you apply zero controls, you're going to begin to get a gravitational torque. And not only that, that gravitational torque is going to accelerate it even further, such that the gravitational torque gets even bigger. It's kind of the classic uh, definition of an unstable system. Okay, but controls do a great job and they keep it vertical, right? And so what I want to really kind of point out with regard to feed forward systems, unless it's an incredibly stable system, um, you always want to have feedback, right? And the premise of a feed forward control system, as we kind of see in this example, is that we presume we know everything that's kind of going on with the system. And very specifically, we presume that we know what these currents are. We're using D and Q in this kind of subsystem we're in right now, but ultimately it's the current that's passing through those electromagnets. Um, and and so our presumption is so strong, it's part of our calculation of what the voltage is for, well, D and Q, or it's calculated here, but ultimately gets reconverted back into the A, B, and C space of voltages that we're going to put on those terminals, right? And that if we're wrong, the calculation is completely wrong, right? And so here's kind of another idea of what PIDs are like. I almost think of them as like rubber bands, and if I were controlling, with feed forward some lever that does something like this, it's almost like my conception of what this lever is that's operating on the controller, that I can do my best to estimate it, but it's good to have something that sees a what's the right word for a divergence between what I think it is and what it truly is, and that applies something that essentially has a restoring action to keep them moving together. All right. And so that's why this idea of a rubber band has always kind of been in my head with regard to what PIDs do. And certainly when they're taught, they often talk about, well, KP is like a spring and KD is like a damper, So that analogy is a useful one. Right. But let's kind of get back to this topic. Right. And so with regard to feed forward, and especially simulation of a motor, where we're applying feed forward, it's by definition almost that we know exactly what the system is, and that we have a controller that certainly knows, the inductances and resistances, and essentially the I'll call it the the description of the equipment. Okay, and and so if things still go unstable even in a simulation, it really means that you are not accounting for the unknown. And if it's on a simulation, the unknown is minimal, right? That the true unknown on this one is essentially a numerical error that takes place in our calculation of various, numbers, that's on the order of like 10 to the minus 16th. Okay, and so in the real world, the wind blows. In the real world, equipment does deteriorate. It's not exactly the same as it was the day before, and certainly not the same it was 6 months ago. And so PIDs come into play, and they really manage that and make sure the overall system does what it's supposed to do. Okay, so anyways, hope that's clear. The the feed forward controls are great, but definitely for them to be successful, almost always you have feedback involved still. All right, and I think just to kind of finish up on one more point. Okay, let's go in here, and I want to bring your attention. Well, let's look at kind of the setting of the of the direct current command is really pretty simple. To save power, we want to drive it to zero, and if it remains zero, its derivative will be zero. So that's kind of easy. Now, quadrature current, of course, is a mapping of torque. And it's basically scales according to this parameter with what the torque is, right? And we already kind of talked about that's why you could be very kind of careful about how you choose a motion command, right? But in this model, drag this just a little bit. I decide to do kind of a numerical derivative, right? And so essentially, here's the creation of a signal that represents quadrature current, and it contains both the current and its first derivative, and we do this numerical calculation of delta U, delta T. Now, a lot of people will look at this, especially a lot of my friends at MathWorks, and they'll say, that's the most dangerous block in all of Simulink, and so certainly they're right, and certainly if you sent in like a step function or something like that into it, the problem is it wouldn't even calculate infinity. It either calculates some super big number, or calculates something that's not a number, and therefore, it's going to destroy whatever your controller's trying to do, right? But, in this example, and to show kind of our tracking of this, that things do work out pretty well because the quadrature current itself is finite, and so is its first derivative, right? And so here's where I just want to kind of wrap up with regard to demonstrating this model, is that the command signal itself that I've sent to make all this work, is a 4-component signal. I'm only using 3, which will be essentially, this is a motion command. So I'm commanding motion of the shaft, the velocity of the shaft, the acceleration of the shaft, and then this fourth one would be the jerk of the shaft. And you'll see that in this case, there is a feed-forward mechanical controller too that's really represented by this, and it's as simple as it can possibly get. That we're just picking off that third component of the signal, which is acceleration, and we're multiplying it by inertia, and that's the amount of torque that we're requesting of our field-oriented control, right? But I want to get into here and really just kind of show you something. I want you to look at these bottom 2 graphs, and don't those look familiar, right? And so again, it's just kind of a confirmation that quadrature current is going to be proportional to that acceleration in this very special case where our inertia is constant, and that the first derivative of that's going to look like this, and we saw that di dt for quadrature current look just like that too. Again, they're scaled a little bit differently based on what the inertia is, as well as what the inductance and flux linkage and number of pole pairs are, right? So anyways, kind of moving forward, we're going to get into mechanics, right? And that usually things are not nearly as simple as what we just looked at, taking acceleration, multiplying it by a scalar number, and knowing what our torque will be, right? And so with regard to, well, I'll just kind of say with regard to building mechatronic systems, there's a reason that mech is in the name, and I'll simply say we're all very fortunate that mechanical engineers exist, okay? And so as systems get a lot more complicated because there can be multiple connections, maybe with multiple actuators, and whatever this link over here is doing really is going to affect, how this one's going to respond to forces and torques, right? And so it's all very kind of complicated, but there's this, again, this, you know, this gift that's been presented to us from our predecessors, you know, and you might be, it might be very important to name, especially like Newton and Euler and folks like that. But essentially, it's this discipline of rigid body dynamics where we can be very predictive of how a mechanism is going to respond to, you know, actuation forces, and we can also be very analytical to understand if this is the motion I want, these are the forces and torques that are going to be required. And it means that I can create a controller for a much more complex and elaborate mechanism that's going to figure out these torques very well in a way that the field-oriented control can kind of operate and deliver on this, right? And so, you know, it's kind of, well, I'll just kind of say it's very impressive how it all works now. And it's that the mechanical engineers really need the electrical engineers because they can create this amazing device, which I'll call the perfect torque generation system. You know, and that mechanical engineers can provide to the electrical engineers this really important mechanical piece too. So anyways, I think the next video where we begin to get into that mechanics is going to be really interesting, and I think it's been set up very nicely as we've kind of worked through how does field-oriented control really work, and the fact that the most important driver on what's going to happen with you know, with the electric motor with this algorithm being applied is the torque. I think that's kind of remarkable, and it's kind of certainly points a direction to let's get into the mechanics next. Thank you.